Welcome all. In this lecture, we are discussing about magnetic circuits. As an introduction, we can start from the definition of a magnet. Any material which possesses the magnetic properties is called a magnet. The property is called magnetism. A permanent magnet is a material where the magnetic field is generated by the internal structure of the material itself. We can also create the electromagnets. In electromagnets, the magnetic field is produced by an electric current. So, we know that if a current is passing through a conductor, there will be field lines generated around the conductor. So, this concept can be extended to the case of a coil. Means if you are passing the current through a coil, here each turn will act as separate conductor. Means there will be field lines around each turns like this. There will be field lines around each turns. It will be acting as separate conductors, and this will form a resultant field lines like this. So this is the case of electromagnet. If you are comparing this with the magnetic field produced around a permanent magnet, they are same. Means if you are passing electric current through a coil, it will act as a electromagnet. So this is the case if the magnetic field lines are allowed to flow in free space or vacuum, and we can provide a material to flow this magnetic field lines like core. So here we are wounding the coil around a core and we are passing a current I. So this will produce a flux or field line and it will be passing through the or flowing through the core material, and the shape will be depending upon the shape of the core. So it can be simply a rectangular or with a air gap length. So the field lines will be decreasing since air gap does not allow much flow of the field lines, and can be also a ring type core. So anyhow, consider this magnetic core material and we are holding a coil around it, and the number of turns is n and the current passed is I. So we can now define magnetic flux. So we told that there will be field lines or magnetic field flowing through the core material. It will be a closed path. So number of field lines or concentration of this magnetic force lines is called flux. Its unit is Weber. If you are looking at the magnetic field lines, we can see that magnetic flux lines are imaginary lines, and it will be always a closed path. It will always forms a closed loop, and magnetic field lines do not intersect each other. And this closed path formed by flux lines is called magnetic circuit. Next one is magnetic flux density. So this is flowing through magnetic field lines are flowing through the core material. So the magnetic flux density is defined as the flux per unit area. So if the cross-sectional area of the magnetic path is A, we can say B is equal to phi by A, where phi is the flux, and the unit will be Weber per meter square, since Weber is the unit of flux and A is the unit, meter square is the unit of area. B will be having a unit Weber per meter square. Next one is magnetomotive force, MMF. So MMF is the force which establishes the magnetic flux in a magnetic circuit. means it is a source which is giving the energy to create this magnetic field lines. So here the source is this coil through which current I is passing. So here the MMF is defined as the product of N into I. Since this is the cause, number of turns into I is the MMF, which is represented by or denoted by the letter F, and its unit is ampere turns. Ampere is the unit of current and turns is the number of turns. So ampere turns, AT, is the unit of MMF. And next is magnetic field intensity or magnetic field strength. It is denoted by letter H. It is the MMF per unit length of magnetic circuit. MMF per unit length. So if L is the total length of this magnetic path, L is the magnetic path length. So H is equal to F by L, MMF by L. Again, MMF is Ni, so H is equal to Ni by L, and its unit is AT by M. AT is the unit of MMF and meter is the unit of length. So next one is reluctance. So we know that this field lines will be flowing, and there will be according to the material. It is depending upon the material. So the material will be offering a opposition to this field lines or this flux. It is called reluctance. Opposition offered towards the flow of flux by the magnetic circuit is called reluctance. So if you are considering the if you are comparing with this electric circuit, in electric circuit current is flowing and the source is an EMF. Here the source is an MMF and the flux is flowing. Okay, so if you are comparing with electric circuit, R is the opposition offered to the current flow. Here it is reluctance is the opposition offered to the flux, flow of flux. So in case of electric circuit, R is equal to M, EMF divided by I. So comparing to that, reluctance can be defined as MMF divided by the flow is flux, so F divided by phi. Again we can say that similar to the case of resistance. Resistance is proportional to L by A. Here also reluctance is also proportional to L by A, means it is directly proportional to L and inversely proportional to A. It is clear that if the length of the path is increased, reluctance will be increased. If the cross sectional area is increased, it will be easy to flow, so the reluctance will be decreasing. So S is directly proportional to L by A. And in case of resistance, R is equal to rho L by A. Rho is the proportionality constant, where rho is the resistivity of the material. So here S equal to 1 by mu L by A. So mu is the permeability, the easiness by which the material allows to flow the flux. So S is equal to 1 by mu L by A, where mu is the permeability of the material and is defined as the ability of material to conduct magnetic flux through it. And again we can define mu as the ratio of magnetic flux density to magnetic field intensity, and unit is Henry per meter. And also the permeability of air is denoted as mu 0, which is equal to 4 pi into 10 raised to minus 7. Next is relative permeability. The ratio of permeability of material to permeability of air is called relative permeability. So if mu is the permeability of a material and mu naught is the permeability of air, we can define permeability of the material mu r is equal to mu divided by mu 0. Since it is a ratio, it is unitless. So we can also say that permeability of material mu can be denoted in terms of permeability of air mu 0 into mu r. So by this equation we can term S as S is equal to 1 by mu 0 mu r A. Sorry, S equal to L by mu 0 mu r A, where L is the length of magnetic path, A is the cross-sectional area of the magnetic path. So if you are looking here, an MMF is there, and because of this, flux is flowing through the magnetic path or magnetic material, core material, and S is the reluctance which is opposing this flux. So if you are comparing with the electric circuit, it is analogous. Here EMF is producing a current, and current is flowing through the electric circuit, and resistance R is the opposition to this current. So here MMF is analogous to EMF, flux is flowing, so flux is analogous to current, reluctance S is analogous to resistance R. The closed path for electric current is called electric circuit. Closed path for magnetic flux is called magnetic circuit. In electric circuit, current is flowing. In magnetic circuit, flux is flowing. The cause of current flow in electric circuit is EMF. The cause of flow of flux in magnetic circuit is MMF. Opposition to the flow of current is called resistance. Here, opposition to flow of flux is called reluctance, S. Current is defined as I equal to E by R by Ohm's law. Similarly, flux phi equal to F by S, MMF by reluctance. Current density is defined as J equal to I by A. Flux density B is equal to phi by A. Resistance is defined as rho equal to rho L by A, where rho is the resistivity of the material. Reluctance is defined as S equal to L by mu A. So with this we can wind up this session. Thank you.